Thank you. So I'm very happy to be here and to visit the lab. I realize that the lab has a connection with the CNRS French research agency through the LAME chair, and since I am a member of CNRS, I'm very happy to be there. I'm very proud. So I was asked by Peter to make an elementary talk. And I am a theoretical physicist, not a mathematician. Therefore, I'm working with mathematicians, some mathematicians, Jean and some others too, so I'm a bit used to the method and the language. But so I won't be, it will be rather a very elementary introduction to a very wide field which interests both mathematicians and physicists since several decades. And what I'm going to present is some, well, just a very short introduction and some ideas and models that I've been studying with two colleagues in Saclay, Bertrand Hénard, my colleague, and Séverin Charbonnier, who just graduated 1 month ago, and Jean Scott, that I met in a math conference and with whom I started to learn and to work. Okay, so this is about what physicists call two-dimensional gravity, and I'm going to explain a bit what physicists and some mathematicians means by two-dimensional gravity, and the relation with random objects which are called random planar maps. So let me first give a very short introduction about what we call continuum gravity. Okay, so continuum gravity, so the point is that physicists are interested since well, more than half a century in constructing a quantum theory of gravity, as we succeeded in constructing a quantum theory of elementary interactions, except gravity. And of course, the starting point for most people is general relativity, which is, as you know, a theory of dynamical space-time. So space-time is curved. It has a Lorentzian structure which embodies a relation between events in space and time, and it's dynamical, namely that its evolution with time is encoded in the Einstein equation, and it's coupled to matter, and so matter interact with space-time as space-time interact with matter in a way which generates gravitational force. Okay, so quantum means that we have to try to quantize this theory of dynamical spacetime, and the possible approach that has been pursued since many, many years is to use Feynman path integral, but over Lorentzian metric. So of course it's something which is a program which is pursued since many, many decades, but there are still some very serious questions. So the simplification that I'm going to deal are from Lorentzian metric to Riemannian metric. That's something which is very common in the field. It started with Hartle, Hawking, and other people. So it's something, there's some hope that as in ordinary quantum mechanics, you can go from Euclidean spacetime to Minkowski spacetime. But it's more questionable in quantum gravity. The second simplification is much stringent. It goes from 4-dimensional spacetime to 2-dimensional spacetime, namely one space and one time. So it's something. It's a simplification. It's not at all trivial that you learn something about real gravity out of that. But first, it's a very interesting problem, physically and mathematically. So it has its own interest, and also it's motivated by string theory, because in string theory, the worldsheet of the string, so the history of a string moving in space-time, is some kind of two-dimensional space-time. So a lot of questions in two-dimensional gravity are connected and even came from string theory. Okay, so we want to construct, so the basic idea is it possible to construct something an object which is at that stage very ill-defined, we want to construct a functional integral, so integral over the space of two-dimensional metric on some Riemannian, some two-dimensional manifold. So it's a curve, it's a complex curve, but so it may have a non-trivial topology, it may have boundaries, it may have cusps. Okay, and so all this complicated problem is encoded is we have a matrix Riemann structure G, and we integrate with some measure on G. And as usual in quantum theory, there is a factor, a phase factor, which becomes a real weight factor in Euclidean space-time, which is the exponential of minus the action of the theory. So the classical action of the theory is taken to be the standard Einstein-Hilbert action Euclidean, so it's the integral over the manifold. This is the volume element. There is a coefficient which is just a cosmological constant, and then the minus 1 over Newton's constant times the curvature. But in 2 dimensions, this is scalar curvature, so the integral of the curvature in 2 dimensions is up to boundary terms, a topological object. So in fact, the important term is the cosmological constant. Okay, so that's the framework, very vaguely.
Construct the functional integrals.
What?
You want to have some kind of Taylor expansion with respect to some parameters. So
I show some method to attempt. The basic idea is that if you can define this object depending on the boundary condition and the topology, you get some function of the boundary condition of the topology, which tells you something about the quantum theory. But of course, quantum theory is invariant under diffeomorphism. So in fact, there are no real local observable. Like in a quantum theory, you have a green function, you have scattering amplitudes, you have expectation value in the vacuum of operators. Those are the basics objects that if you know a bit of quantum theory, there is a well-defined mathematical formalism for dealing with that. And in quantum gravity, everything is much more delocalized. Everything is delocalized. Okay, so I give you some example. Okay, so, well, in quantum theory, in fact, all the story started with a famous paper by Sasha Polyakov when he was in Moscow, who showed in 81 that if you start from this path integral over two-dimensional metric, you can use diffeomorphism invariance to show that any metric which is here considered as a quantum object, so it's a random variable we want to integrate over. You can always find a system of coordinates where it's up to a conformal factor, conformally equivalent to a fixed background classical metric, up to moduli which characterize the conformal structure, the conformal class of the set of metric. Okay, so this corresponds for a physicist in physicist language to gauge fix local gauge symmetry. So local gauge symmetries are diffeomorphism. So this is a choice of gauge, and this is the remaining field we want to integrate. So this is a random quantized object, and we reduce that to integrate over quantize the conformal factor, which is a scalar factor, so it's much more simple. It has no spin. Okay, so this conformal factor is called the Liouville field, and the reason is that Sasha Polyakov shows that, in fact, by some argument of quantum field theory, that, in fact, the natural quantum action for this conformal factor is very simple. So it's given, so this is a classical action for a field living in a background classical metric. So now we have a classical gravitational field and a quantum field living within this background field. So the action contains, so it's usually it's the integral over space-time of a Lagrangian density, and the Lagrangian density contains a term which is the gradient of phi squared. These are in fact covariant derivative, of course, with respect to the metric. So this is the action of a free field, a free scalar field that if you have learned a bit of quantum theory, that's the first things that is found in the books. There is here a term which is exponential of gamma phi, which is, well, it's the area term. So this is the renormalized cosmological constant. But there is a non-trivial coupling of this phi with the scalar curvature. The background scalar curvature with a factor q. And Polyakov shows that by an explicit calculation. This was formalized by many people, by David, Smith, Distler, and Cowell later, by Knish. There are some famous papers by Knishnik, Polyakov, and Zamolodchikov in 88, some paper, etc. So there is now a huge literature. So the point is that the non-trivial dynamics is contained here. It's a non-trivial coupling between the classical metric and the quantum field. And for consistency condition, this factor q is related to this gamma phi here by a simple algebraic relation. And moreover, both so gamma and q are not free parameters. They are fixed by a relation which fixes what is the conformal charge, the central charge of this. Because this is a conformal field theory, and the conformal field theory is characterized by a conformal charge. It's a number characterized of the quantum field. And this is the conformal charge of the Liouville field. And the conformal field charge of the Liouville field has to be equal to 26. It's something that comes from the gauge fixing, minus the central charge of matter if you have additional matter fields, other quantum fields coupled to the gravitational background. So in fact, the theory is fixed by its matter content. And if there is no matter, so we are just quantizing on gravity, the central charge of Liouville theory is 26. This fixes Q, and this fixes gamma. So the theory is completely fixed. So it's a very interesting.
26, the Lorentz 26 comes from 24. Or something.
Well, you can view it. Well, it comes from the calculation of the central charge of the system of ghosts. So but you can view it as 20. Well, I think you can view it as 26 is 1 plus 12 times 2. Do you like this this identity? Okay. That's the way it is.
Dimension of the Lorentz and lattice, I think that's the same reason.
Yeah, this one comes from the fact that if the ghosts were scalars, this comes from the fact that the ghosts are not scalars, but they are tensors. And this too comes from the fact that you have ghosts in the holomorphic sector and ghosts in the anti-holomorphic sector of the theory. I think that if you know a bit of conformal field theory, these words would tell something for you. If not, I can explain in private. Okay. So,
What is mu?
mu it's a cosmological constant. So this parameter basically controls the size of the surface. You quantize. So you have a surface, and the metric fluctuates. So you can ask what is the quantum expectation value of the area of the surface. In other words, what is the expectation value of square root of g? This is the total area. What is its expectation value? So it's the expectation value in the vacuum. Okay, and this object has a dimension of an area, and so you must have a dimension full parameter in the theory, and the only dimension full parameter is this. So in fact, this is proportional to 1 over mu r. So the question is what is the number, and what is it for surface with topology? Okay. So mu basically is the dimension full parameter that tells you what is the expectation value of the area, in which vacuum you are, if you want. Okay. Okay, so there is a very large literature on the Liouville theory. I won't talk about that, but I will explain how some physicists and some mathematicians are trying to build a Feynman path integral for two-dimensional metric using a different method which consists in discretizing this. So, discrete gravity. So, the idea is, so it's a game that started by replacing a continuum metric by a random lattice. And it started in the 80s by these gentlemen. So somewhere in Kazakov, Migdal were in Moscow, Fröhlich was in Zurich at the moment, and I was in Princeton, in fact, when I did that. But so the idea is basically that instead of summing over all possible metric on the surface, we assume that the space-time is discretized. So we replace it by some kind of lattice. But the lattice will be random because the metric has to be a quantum object. So the idea of discretizing space-time is, of course, an idea which has been very successful in ordinary quantum theory because it's used in lattice gauge theories, for instance. In fact, it's an idea that I think goes back to before World War II and was suggested by maybe Heisenberg. So it's a very, very old idea. Okay. So the question is, can we find nice way to discretize space-time by some kind of random lattice? And here, for instance, what I've drawn is a random planar quadrangulation. So this is, in fact, a two-dimensional lattice, but if you are, it's a bit fine, but if you are close enough, you will see that, in fact, you have vertices, and the faces of this lattice are always squares. So there are some strange squares like this one, but this is a square. Okay. So this surface is made by gluing squares, but of course not to build a regular square lattice, but a lattice where you have a lot of curvature. Here you may have many squares glued, here you have very few. So this is a curved discrete space. Okay. So one way to study the statistics of random maps, the first one, is to just study, for instance, a random planar quadrangulation as just a combinatorial object. So for instance, you consider all the possible ways to glue squares in order to build a sphere, for instance. Okay. So this is now called random planar maps. Okay. So this is a piece of a map built out of squares, and I call it planar because it has a global topology of a sphere. We can choose to be a torus or something else, but here it has a topology of a sphere. Okay. So, for instance, one of the first ways to study this kind of statistics of this object is to take the dual graph. Because if you consider the dual graph, where you glue faces, of course, since the faces are squares, the vertices of the dual graph are four-valent. Okay? And therefore, there are many ways to use this. So, for instance, we can show that those graphs, those dual graphs, are just a Feynman diagram of a random matrix model with a phi-4 interaction. So you take a random matrix model, you integrate over all possible matrices which are emission, n by n, the emission matrix, and you get exponential minus 1 over, basically, trace of m squared plus g trace of m4. And you expand in G, and the perturbation theory, you ask about the perturbation theory. The perturbation theory of this model, when you integrate over a matrix, are just these graphs. And so the method of, the mathematical method of studying random matrix model can be used to do that.
So far you have a graph without any metric. So you think that all edges, they're just edges?
Yeah, basically you can state that, in fact, there is a matrix. You can consider this graph as a matrix with unit lengths. Each edge has the same length. And for instance, using, this BEPZ is just one of the very first papers using matrix model to study this kind of things. It was a paper by Brezin, Itzikson, Parisi, and Zuber. But also there are older methods initiated by a Canadian combinatorist from Canada, Tutt, in the 50s and beginning of the 60s, which are combinatorics methods. So everything is, and for instance, these French mathematicians devise a bijection between this kind of graphs and trees, random trees, which allows to study the statistics of distances on this tree, which is not at all trivial. So you can ask what is the average distance between 2 points just by taking the minimal length path, the path with a minimal number of edges. So this is a metric graph, but with a metric which is discretized. Okay, so this is a discrete graph, and what physicists are interested in is making space-time continuous, as the space-time we live in at our scale, by taking a random graph, but taking a limit where it has a very, very large number of vertices, so that's viewed from at a large scale, it's continuous space. It's quantum, but continuum space. So the idea is to take a random quadrangulation, for instance, and fix the genius of the surface. So for instance, genius 0 is a planar surface, and let the limit of number of points going to infinity. And letting the limit of points of vertices going to infinity, well, in physics, in statistical mechanics, it's called taking the thermodynamic limit of a system. And taking the thermodynamic limit of the system, you only have interesting things from the point of view of me, for instance, if you are at a critical point where you have infinite correlation lengths. So looking for a critical point means to look whether there are singularities as a function of g in this integral. And there are singularities, there are very interesting things. Okay. And so this can be studied. So for instance, by this method, well, here is the simplest of the many results we have, but it's very important. You just consider what is the number of maps with a size n. And so this is called z, here it's called z of n, it's a partition function as a function of the size of the surface. And it grows like a constant to the power of n, and the constant depends on the model. But then there is a power, a correction, which is some power of the number of vertices, which depends only on the genius of the surface. Okay? And this is something that can be computed using matrix model or combinatorics, but it can also be computed in Liouville theory, thanks to the work of Knizhnik, Polyakov, and Zamolodchikov. And so if you, here I'm walking, so this index, this exponent, well, it's re-expressed in terms of something which is called the string exponent. It's just terminology. Okay. So here the string exponent here is -1/2, and this is the prediction of the string exponent that comes from Liouville theory, and it's related by this. So it's a solution of a second-order algebraic equation which connect gamma strings to the central charge of Liouville theory. And for pure gravity, CL is 26. You put this in this formula, and you get -1/2. So this is a prediction of, for instance, matrix model. This is a prediction of continuum two-dimensional gravity, and this agrees. So that's one of the first achievement of the two methods. But now one has many more results. Okay, so I won't say I could give many seminars on these random maps, and I'm sure some of you are aware of that. So I'm going to turn to some variation, but I think important variation of this model, which consists in decorating the map, so changing the length, for instance, instead of having fixed length. So the first one are Strevel graph, it's something which was started by Bertrand Hénard, and the other one is what's called random Delaunay triangulation. So we are trying to construct random graph out of the random Delaunay triangulation in the plane. So first, let me discuss random Strevel graph. Okay. So as I explained, random graph can be dressed by, for instance, changing the length. And this has the advantage of considering a continuous space of metric instead of a discrete space. If you consider, just random quadrangulation, so each quadrangulation is isolated. You cannot deform it continuously into another triangulation. While with a graph which contains some continuum degrees of freedom, you can have a continuous space of metric, which has some advantage. It might be more complicated to compute, but sometimes it's easier to compute. So Strebel graphs are an example. Okay. So what are Strebel graphs? Strebel graphs are graph. Fat means that they have drawn on the surface. Instead of being 4-valent like the one I showed, they are 3-valent. Okay, and you have lengths associated to each edge. So, for instance, here is an example of a trivalent graph drawn on a torus. So, in fact, this trivalent graph has only 1, 2, 3, 4 vertices, and it has 1, 2, 3, 4, 5, 6. So it has, if I count well, 6 edges, and each edge, to each edge is associated a length which is a positive number. And the idea is to consider the sets of all such graphs. So we have a triangulation, a trivalent graph, and lengths. Okay. So you see on this example, for instance, that you have faces. And to each face on the surface is associated the perimeter, which is just the sum of the length of the edges of the face. Okay? And so this kind of graph have been, they have been proposed by Strebel, a mathematician, and they have been used for many purposes, in particular by Bob Penner and by Maxim Kontsevich, for a very interesting purpose. So what we did is just some kind of application for our purpose of this method. Okay. So what you can do is that you can consider all the Strebel graph, but you may consider also. So this is a set of Strebel graph. It's the data of G and lengths, and you can either integrate over all the lengths or fix the perimeter of the face. So you have faces, and to each face is associated a perimeter. The perimeter is fixed, but so this fixes constraint between the lengths. Okay. Okay. So the point is that I'm very sketchy, but Strebel, and then there are some theorems by Strebel, and then by Kontsevich, which relies on the idea that there is a mapping between the space of Strebel graph with given number of vertex or face and a given number and a given genus, and the moduli space of Riemann surface with fixed genus and puncture and decorated, namely you have a positive real number associated to each marked point. So you understand, you have, well, here is an example. So this is a Riemann surface with 4 marked points. The moduli space is a space of complex structures of surfaces that are equivalent by an analytic mapping. And in addition, you associate a length L, L1, L2, L3, N to each point. But the point here will correspond to a face of the Strebel graph. So in fact, there is a Strebel graph that I haven't drawn here, but you can embed a Strebel graph inside this surface. This was the kind of things that was drawn just before. Here, this is a Strebel graph, and think about each face as carrying one point, and this point carries the perimeter of the face. Okay, and consider the complex structure associated to this. So you forget about the Strebel graph, but you keep the center of the face or some point within the face and the perimeter. In fact, there is a non-trivial mapping, the construction between that, which is provided, if I understand a bit the theory, by Strebel's quadratic differential. So that's geometry. I won't talk about it. So this is standard mathematics. Okay. So you may consider the space of Strebel graph, and this is the space of the moduli space of the space of decorated puncture surface, the moduli space. Or you can fix, in addition, a strata, so you can fix the length associated, the perimeter, so the positive length associated to each vertex. And then you get just representative of the moduli space of marked surface, but with no decoration. Okay. Okay, so there is a mapping between the measure on Strebel graph and the measure on moduli space of decorated marked surfaces. So for a natural measure on the space of Strebel graph is just you take the Lebesgue measure. So you integrate with a flat measure on all the lengths, the positive lengths of each length, and you just introduce, if you have fixed the perimeters, you just introduced a Dirac, a constraint. That's the sum of the perimeter is equal to L. Okay.
What does it mean? Means it's a phase contractor?
Pardon?
What does it mean? The second, the delta measures.
The second measure is just that you fix the perimeters to be LF. So instead of having the as many edge, as many variable, as many lengths as you have edge, you have independent edge, you have number of edges minus the number of face. It's still a number, but it's a number which grows like 2 times the number of vertices instead of 3 times. Okay. So the theorem, so there is a famous theorem by Kontsevich which said that there is a relation between the measure on this somehow trivial Lebesgue measure on Strebel graph and a measure which is constructed on the modular space and measures out of Chern class, namely 2 curvature forms on the moduli space of decorated Riemann surfaces. Okay, so I'm not going to explain that. I think you know that more than me, but basically, so there is a mapping between the phase. And so in fact, this measure is an integral, is a measure on the perimeters times some combination of products of linear combination of Chern classes associated to the different marked point. Okay, and Kontsevich was able to relate this, the integral over the whole moduli space of these forms to what are called intersection number. So therefore, with some explicit results which are contained in the paper by Kontsevich and from other people, you can compute, you can get information on the statistics of large Strebel graph. So the idea is that we are interested in large Strebel graph because there's some kind of deformation of planar triangulation or trivalent triangulation, but we can rely on mathematical work with explicit formula to get what interests us. Okay, so what we are interested in is the space of Strebel graphs when there is a large number of vertices, namely a large number of faces, because that's the continuum limit that interests us. What Kontsevich theory and all the results people are interested in getting information on moduli space with a finite number of points and the finite number and finite genus, but we are interested in finite genus, for instance, g equals 0, but the limit when there is a large number of vertices, large number of faces, and this was apparently this had not been done. Okay, So what we get basically is the following fact. So there's a long calculation that are available in a paper by Séverin, Bertrand. I just give one of the results. The result is that the volume of the space of Strebel graph with fixed perimeter. So here L is just the fact that we consider Strebel graph where the perimeter of all the face is the same. So there is still a unit of length, but it's a unit of perimeter. Okay? So this volume, it corresponds to, if you want, to the number of Strebel graph with fixed perimeter and n faces. So it grows like a constant. So you can check that there is something which depends on L, but basically there is some number, mu, which is 1.9. It's a solution of some equation involving some Bessel function. So it grows like some constant times the number of faces. Well, there is a factorial here simply because in this calculation the points are marked, so there is a they are distinct. While in quantum gravity they should be the same. You have no way to. So this n disappears, and there is an exponent to the power minus 7 divided by 2. So that's the same exponent that's the one I showed coming from the calculation on planar maps. Okay, so that's important. So this exponent minus 7 divided by 2 for Strebel graph with the topology of the sphere is the same that the one which was obtained by planar maps and by Liouville theory. So it shows that although it's a model which is more complicated, it belongs to the same class. It has the same continuum limit.
That's only for sphere, not for us genus.
For higher genus, I think it's, the results will be valid too. First, there is no reason that it's not.
It's different constant.
Yeah, of course. Then you are going to be minus 7i half, and then plus the genus minus 1 times the 5 half, I expect. Okay. I have to check it what we computed. Whether I think we have computed it for the torus, but it should be not very difficult. Well, it might be lengthy and tedious, but we have no reason to expect that if you get the correct result for the topology of the sphere, it's very difficult not to continue to extend the results to higher topologies. It's not a mathematical argument, but it's a physical intuition. Okay, so now let's go to the random Delaunay triangulation, because this model is geometrically interesting. This model is geometrically interesting because we start to deal with how a random abstract planar map can be embedded in the complex plane. The results we got before were somehow combinatorial result. Okay, so this is going to be very elementary because first, I presume you know what is a Delaunay triangulation. So I'm considering in the plane, and I just have a set of points in the plane. I hope it's visible from far away. It's barely visible. Maybe one should switch off a bit some light. I'm sorry. Yeah, okay. So here you have some points. Here it's a random distribution of points, and as you know, you may consider the Voronoi complex obtained by considering all the cells of points which are closer from a given point than the other neighbors. This is a Voronoi complex. Okay, I'll have to use a bigger. And you take the dual of this, so you take the Delaunay triangulation. You see, and what you get is a set of triangles generically joining vertices of the initial distribution of points. Okay, and so to any distribution of points is generically associated a unique Delaunay triangulation. So you may construct a triangulation out of a distribution of points. So now, of course, the question is, you may have many different kind of distribution of points, class of distribution of points, which lead to triangulation which have completely different statistics. So here, let me give two examples. I hope this is a bit more visible. So let's look at, it's very, no, it's totally invisible, except maybe, okay. So well, what I can just state is that if you take a random distribution of independently distribution point, namely a Poisson process, you get something interesting. A lot is known about random Delaunay triangulation, but basically the cell, well, it's not visible, but the cells have, the number of edges of the cell fluctuates, but not too much. It fluctuates between 2, or well, between 3, which is the minimum, up to, the Voronoi cells, and 10 or something like that, but then they decay. While if you take a distribution of points which is, well, inspired by Liouville theory, you have points and you may have very dense distribution of points and very region where it's very dense and it's very sparse. And the property of a Delaunay triangulation has constructed out of this distribution of points, inspired from, for instance, from Liouville quantum theory, is very different. And that's what we want to inspire. Okay, so I'm sorry for this picture, but the next one would be better. Okay, so, well, another criteria to construct the Delaunay triangulation, if you have a set of points, is that when you have a triangles, you can construct the circumcircle associated to each face, each triangle, and it's a well-known fact that the triangulation is Delaunay if you consider a triangle, the associated circumcircle, all the other points are outside the triangle. It's somehow elementary. So this is typically you see that this is a Delaunay triangulation locally, and if you suppress this edge and transform it into this edge, then this face has a big circles that contains many other vertices. So that's one simple way to see that it is not Delaunay, without measuring distances, only looking at points. Okay, and the interesting fact of this, which is quite elementary for mathematicians, but which is when you consider triangles and circles, if you apply a Möbius transformation on this distribution of points in the plane, namely a PSL2C transformation, circles, a triangle is mapped onto another triangle, but the circumcircle is mapped onto another circumcircle. And if the points in the initial triangulation are outside this circumcircle, in the mapped triangulation, the point will be still outside for topological reason. And therefore, the Möbius transformation of a Delaunay triangulation, although the distance changes in a highly non-trivial way, it's still a Delaunay triangulation. Okay. And so that's something that we are interested in because Liouville theory is a conformal field theory, so we were looking with Bertrand to ensembles of triangulation with good global conformal property in the plane. So this is a way to realize. The set of Delaunay triangulation is naturally embodied with SL2C invariant properties. Okay. Another way to view that is that the natural parametrization of Delaunay triangulation is you consider a triangulation, and to each edge you associate an angle associated to the edge, which is the angle between the segments joining a vertex here to the center of the circumcircle of the two triangles that are adjacent to this edge. This angle is invariant under conformal transformation, and therefore it's natural to study the set of Delaunay triangulation by considering as variable if you want, the combinatorial structure of the triangulation and the angles associated to the edge. So the angles here are going to play the same role for Delaunay triangulation as the lengths are associated to the Strebel graph. They are also continuous triangulation, continuous variable. So that's the idea. Okay? So now, well, I'm making a very short summary of what we did, but Delaunay triangulation are an example of what is called the theory of circle patterns. And circle patterns is a theory of, geometry of circles that intersect themselves. And the circle patterns are a generalization of the well-known theory of circle packing, where you have circles, but they can only be tangent to each other. Okay? And there is a theorem that by Rivin, which states, in fact, that there is a mapping between abstract circle packing and Delaunay triangulation. So if you consider a triangulation and you associate an angles to each edge, there is basically a unique Delaunay triangulation up to Möbius transformation, provided that the angle satisfies the following constraint. First, if you have a triangulation, you consider a vertex, you have edges associated to each the adjacent edges to this vertex. First, the angle have to be positive. Second, the sum of the angles have to be equal to 2 pi, and geometrically it's quite obvious. It means that the triangulation is locally flat here, if you think about triangles. And there is a slightly less obvious constraint, which is now if instead of considering the edge that's associated to curve going around a single vertex, you may consider a curve on the dual lattice that goes around some ensemble of vertices. So this is a curve on the dual Voronoi complex. You consider all the edges that are dual to this curve. So they are the red one. You consider the sum of the angles associated to all these edges. This has to be greater or equal to 2 pi. And this comes also for the geometry of triangulation in the plane. But now if you consider just an abstract triangulation, so you know which vertices are connected to which vertices, you are given angles associated to each edge satisfying those constraints, then it can be realized as a Delaunay triangulation in the plane. So you can consider Delaunay triangulation either as abstract combinatorial object or as geometrical object in the plane. Okay, so now the question, which is a question similar to the question we had for Strebel graph, is there a natural measure of integration over the space of Delaunay triangulation? So the measure has to depend only on the angles if we want to have a SL2C invariance property for the Delaunay triangulation in the plane. And so a natural measure is the analog of what was for Strebel graph. You sum over triangulation with a uniform, so you say each triangulation has the same weight. And then you integrate with the flat Lebesgue measure on the angles with the same constraint, that the sum of the angles around the vertex is equal to 2 pi, and the sum of the angles around any curves has to be larger than 2 pi. So these are linear constraints, and this is a Lebesgue measure. Okay, and of course, this measure on this space is very easy, but if you pull back this measure on the space of distribution of points, you get a highly non-trivial measure, because you know that to any distribution of points, for instance, here is a random distribution of points in the plane, you can construct a Delaunay triangulation, and the weight associated to this Delaunay triangulation with these angles, this is just the space of Delaunay triangulation. It's the space of points quotiented by SL2C. You get a measure which depends on the density measure which depends on the position of the points, which is obtained by a Jacobian of a change of variable from this flat measure to this measure, and this is an object which is non-trivial. It's just a Jacobian of a transformation, but it's global. It depends on the position of all the points. Okay. So we have several results, and maybe I presume some of the results were already known by mathematicians, by geometers. But first, well, okay, I'm just skipping a lot of all the detail. But first, this measure. So this is Jacobian, so it can be written as a determinant. It's a determinant. But one can, by some work that it's a law. It's a Kähler measure. So this measure is a determinant of an n by n matrix, where n is the number of points up to SL2C transformation. It means that in the previous triangulation, you can consider that the point 1, 2, and 3 are fixed by S. So this can be 0, 1, and infinity, for instance, and you integrate over the position of the other point. So here, for instance, you integrate over 4 points. And this measure is a determinant of 4 by 4 complex matrix, Hermitian matrix. But this matrix is the matrix element form a two form, which is a Kähler form. So the space of Delaunay triangulation can be embodied with a Kähler structure. Okay. So we studied this measure. It's nice, somehow elementary geometry, and we showed, for instance, that the Kähler form, so the two form, which is the form in terms of the position of the vertices, can be written. So this is a complex, the two form. It can be written as a sum over the faces of the triangulation. So it decomposes. It's not two non-local. It's a sum of the combination of each triangle of the triangulation, and it can be written, for instance, as a sum over each triangle, and then you have this combination. It's d of the log of the length of the side, wedge d of this length of this edge, plus, so this wedge this times d this times wedge this d times this wedge this plus this wedge this plus this wedge this. So it has a simple structure. That's a bit surprising because initially we had something that depended on the angles, but we can re-express it in terms of the length of the distance using trigonometric identity for triangle. So the kind I learned in high school long ago. Okay. Now, the fact that there is a Kähler structure, in fact, can be viewed from the following fact. To each Delaunay triangulation of the plane, we can associate a constant curvature, a constant negative curvature surface living in hyperbolic three-dimensional space. In the following way. It's a neat combinatoric structure. Okay. So, first I consider the plane, and this is a piece of a Delaunay triangulation or a general triangulation, and here is a triangle. Now, imagine that think about this plane, labeled by complex coordinate, as the boundary of the Poincaré upper half space. So I had an additional eighth variable, positive coordinate, and I embodied the H3 by this standard metric. Okay, so there is now a distance here, and now think about that. This triangle has a circumcircle, and I consider the half sphere above the plane. And I consider a half sphere for each triangle. So I get a collection of half sphere, and I consider, so here I have and I consider just the section of the half sphere associated to this triangle, which is above this triangle. So I get some kind of cupola. I have a cupola here, and I'm going to glue the cupola for all the triangles. And I get this kind of surface. I don't know if it's visible. I had some color, but the color is not they had nice color, but they do not pass. Okay. So I don't know why. Maybe it's because of the. Okay. Well, you get the idea. So you get a surface made out of gluing, arches. So it's a bit like in a souk in a Central Asia or a Maghreb country, but if you think about this as a two-dimensional surface living in three-dimensional hyperbolic space, this is a constant curvature metric because it's made out of hyperbolic triangles glued along geodesics, and they are punctured here when the surface touches the boundary. So in fact, the surface here is a constant curvature surface with puncture. So it's a class, it's just an element of the moduli space of constant curvature, of puncture, of the puncture sphere sense. Okay. And so the space of Delaunay triangulation can be associated with the boundary, the completion of the moduli space of the sphere with n boundary. Okay? And on this, the Delaunay triangulation, the measure on Delaunay triangulation defines a measure, and it defines a Kähler structure. So what is this Kähler structure? Well, after some calculation, we discovered that in fact, the Kähler structure is something which is not new. It is just the Weil-Peterson Kähler structure on the moduli space. It's not obvious, but for us it was not obvious, but it turns out that the measure we have on the Weil-Peterson is just the volume form associated to the Weil-Peterson in some coordinates. Okay, so in fact, again, if we want to know what is the volume, the number of Delaunay triangulation with our measure, we can rely on results from mathematicians. Because we just need to know what is the volume of the moduli space of curves with marked points with the Weil-Peterson volume form. And fortunately for us, well, Peter the Graph, I think, was the first to compute this. It had been followed by some other famous mathematician. But the result is that the volume of the moduli space of surfaces of genus G with n marked point, if you work out the result, grows like a constant times the number of punctures times n to some power, and this power depends on the genus, and again it's the same 5g minus 7 divided by 2 that we obtained in the different model. So again, we get the same string exponent and the same Nishnik-Polyakov-Zamolodchikov exponent than for planar random map. So also we have models which are not equivalent, they are not the same model. They have the same continuum limit when the number of points or the volume of the surface goes to infinity. Okay. So the result seems simple, but it requires some work to show that. Okay, so it's just, well, we have a lot of interesting questions, we have a lot of other results, but I just want to give you a taste of why this is interesting. So how much time do I have left?
You have like a few more minutes.
Okay.
Just only a few, like it's...
Yeah, okay. So then, well, I wanted to just say a word about the ongoing work that I'm doing with Jean Scott, but since Jean presented it in some lectures last week, some of you have been there. So I will just make a flash of what we are trying to do. This Delaunay triangulation, if you view them as triangulation in the plane, so I forget about the fact that they are a realization of the moduli space of curves, but I think of them as, geometrical objects in the plane. there is an interesting remark which relates them to the geometry of and the statistical mechanism of isoradial lattice. Because one can check that if you take a random Delaunay triangulation and you assume that the distribution of points is very special and is such that all the circumcircle have the same radius, so it's what's called an isoradial triangulation because all the triangles have the same circumradius, then the triangulation is called isoradial. And isoradial triangulation have a very interesting properties that have been studied in particular here. So first remark, this D operator, which is it's a n by n matrix, which are the matrix element of the Kähler operator in the general case. So it's an Hermitian matrix for isoradial triangulation. If the triangulation is isoradial, it becomes just the Laplace-Beltrami, the discrete Laplace-Beltrami operator in the plane up to 1 over r squared, but r is just the radius of the same radius for all triangulation. So if one can study this model by considering that it's a deformation when the triangulation is not isoradial of an isoradial triangulation. And isoradial lattices are very special. They are very special because the Laplace-Beltrami operator and other operators like Dirac operators defined on such lattice have very interesting properties, which have been studied by mathematicians and physicists. Basically, they are interesting because isoradial lattices are lattices where the concept of discrete analyticity can be defined in a meaningful way. So I have functions which are defined piecewise linear, so you replace ordinary derivative by finite difference, but still you can define the concept of analytic function, and they have the same properties. For example, it's known that in general, analytic function, so a function is analytic, its derivative with respect to z bar is 0, and if a function is analytic, it satisfies the Cauchy theorem around the closed circle is 0, and also it satisfies the fact that the integral of an analytic function is analytic if you don't turn around a pole. Okay, so these are very simple, and it turns out that they are true on a discrete lattice. So here is an example of an isoradial lattice, and isoradial lattice often can be embodied with a bipartite structure, so you have vertices which are two colors, and the center of the radius form also another isoradial lattice, so in fact it has a lot of structure. And in particular, many people, starting by Castelline and some isoradial, have been used in statistical mechanics. And Kenyon has studied a lot this kind of isoradial lattice. Okay. But also here, for instance, it's well known that the famous, solution of the Ising model in 2 dimensions, which started with Castelline and has been studied, comes from the fact that the Ising model has special property when it is defined on an isoradial lattice like the square lattice. The square lattice is obviously isoradial. And for instance, the proof that the fact that the critical Ising model is critical, mathematical proof, uses heavily this concept of discrete analytic functions or the properties of okay. So I think I will not detail more, but the point is that basically, well, okay, I won't explain, but this is a concept of discrete analytic function. What you want?
No.
What? I stopped.
Time left.
No. So I want just to say that with Jane, we started to address the question: is what's happening when you deform a discrete analytic function, a discrete lattice, isoradial lattice to form a non-isoradial lattice, but Delaunay. Jane discussed the various Laplacians that can be defined. We have some results that he presented just during her last lecture briefly, but she presented a lot of method of calculation. And so there are a lot of, I think, interesting things and interesting issue, both for physics and for mathematics, to be done with such object. Okay, so this is an example of what we have been doing, and thank you very much. Yes?
The reason for this model, for all these models to be in the same universality class. So there should be some symmetry behind this, or what?
Well, for a physicist, physicists are, since the work of Wilson and other people in statistical mechanics and the theory of critical phenomena, are very, used to the concept of universality, which means that when you have a model of statistical mechanics and when there is a critical point where they are expected to have a non-trivial continuum limit where you can more or less forget about the detail of the discretization because the correlation length is very large, then in general this continuum limit should depend on very, very few parameters, which are called universality class. And usually universality classes are just discrete objects. So you have a universality class for the Ising model, and its property depend only on the dimension in which the model lives. So there is a universality class in 2 dimensions, a universality class in 3 dimensions, but the same universality class for the Ising model on a square lattice or a triangular lattice or honeycomb lattice. So when you think about the 2-dimensional gravity, up to now there is only one sensible continuum theory, which is Liouville theory. So we expect that if we construct a model which has a continuum limit, unless the deformation is very strong and we add other degrees of freedom, we should get the Liouville theory. The question is, can we prove it? And can we learn something about this continuum limit by using discrete models? And some results on the continuum theory first came from discrete model before being derived using Liouville theory. So that's why it's natural. It's not so surprising that we get for these different models the same continuum limit with the same -7 half, for instance, exponent. But it doesn't mean that we are just checking once more something which is obvious. It means that it's interesting to look at this question. Okay. Yes?
For instance, in the case of Ising,
yes.
Can one find the stress energy tensor or something like it in discrete? Is it possible?
Yes, it's possible on square lattice. Well, there is huge literature on the Ising model on lattice, on isoradial lattice, and it's possible to define a stress energy tensor on regular, fixed lattice. The kind of issue that I'm addressing, for instance, with Jane is it possible? I think it's possible, but what are the properties of a stress energy tensor defined on a random lattice? And less is known in this field. But in a discrete case, in the fixed lattice, I think for many models it's possible. I think I saw a paper by Smirnov and his colleagues in Switzerland on that and many others. So it's possible, yes.
I think we can continue the discussion near the food.
Okay.
Thank you.
Thank you.